Our next lesson is Acceleration 3 on Calculus of Motion. And in this lesson, we're going to look at basically three things. We're going to look at motion and calculus. We'll look at differentiation and integration, those calculus techniques that you use to do this. And we'll look at motion functions. And just as a note, this lesson, we will teach you basically anything you need to know for this course as far as calculus. If you've taken calculus before, then a lot of these techniques we'll use should be very simple for you. If you're taking calculus now, you've probably seen some of them, maybe not all of them. And if you haven't taken calculus, then, as I said, we will teach you everything you need to know for what we have right here. That's what the second section on differentiation integration is on. So first, let's talk about motion and calculus. So in our first lesson on velocity, we noted that the slope of a distance versus time graph is the velocity, because velocity is the rate of distance, that is distance versus time, and the slope is also the rate. That we sort of said, if we have a distance versus time graph, distance up here and time right here, that if we have some object that has a velocity, so its distance is increasing, that the slope of this is rise over run. The rise is distance, the run is time, and so distance over time is the slope, but that's also equal to velocity. And so then the slope is equal to the velocity here. It also turns out, we didn't talk about this, but if you have a velocity versus time graph, that the slope of that will give you the acceleration, because acceleration is the rate of velocity, the change in velocity. If I have a velocity versus time graph, and my velocity is increasing right here, the slope is rise over run. The rise is in velocity, that's your y, divided by the run is time. Change in velocity over change in time is the very definition of acceleration. And so the slope of a velocity versus time graph is the acceleration. So excellent on that. So moving on here. Now in the lesson after that, we also said something else, that if you look at the area underneath the graph on a velocity versus time graph, that will give you the distance. And so we said, if you have some graph right here, and this is said velocity versus time, and you basically find the area underneath that graph, that area right in there is basically going to be the distance. Because in this case, well, it's basically we're sort of doing it backwards from what we did before. It also is true that if you have an acceleration versus time graph, that you look at that right there, that if you look at the area underneath that graph, that area is going to be the velocity. And so we haven't really proven it yet, but this is what we know for right here. So if you have a velocity versus time graph, if you find the area underneath that curve, that'll give you the distance. If you have an acceleration versus time graph, the area underneath that curve will give you the velocity. And the slope of a velocity versus time graph is acceleration. The slope of a distance versus time graph is velocity. So this is what we have so far. And so let's keep on going on this. So here's what we can say. That this means we can move between a function of distance, a function of velocity, and a function of acceleration by using slopes and areas. So if we start off with a distance versus time graph, and we want to find from that distance versus time graph basically what the velocity is, well, we can go from distance versus time to velocity this way by using the slope. Slope gets us there. If I want to go from velocity to acceleration, I can do that by using the slope of a velocity versus time graph. If I want to have a velocity versus time graph and I want to get the distance, I have to find the area under a velocity versus time graph gives me the distance versus time. If I have an acceleration versus time, I want to find the velocity, it's the area underneath that will get me over here. It basically sort of makes a little bit of a cycle. The slope of a distance versus time is velocity. The slope of velocity versus time is acceleration. The area underneath an acceleration versus time is velocity. The area underneath a velocity versus time is distance. And so that's sort of what we've got there. And so this is sort of what we have to start with here. Now, on to calculus. Calculus is a branch of mathematics which studies rates, that is, changes in things. And it gives methods for finding the slope and area of any function. And so, with a few sort of detail exceptions, basically, if you can come up with a mathematical function, in the case of physics, we're typically going to use functions of time, for what we'll do in this section right here, that you can use calculus techniques, which we'll talk about later, to find the slope of any function at any point. If I say I've got a function which is, f of t is equal to 14t to the 19th plus 13t to the 17th minus 76t to the 5th plus pi, and I want to say what's the slope of that graph whenever t is equal to 105, you can figure it out without actually too much work, which we'll see in a little bit here. So there are two techniques that we will use. To find slope, we're basically going to use something that's called differentiation. So differentiation of a function, f of t, gives us the slope f prime of t. I don't know if you can sort of see it there, but this is the notation here. If we have f of t like this, its derivative is f prime of t right that. If you took a second derivative, that is, you took a derivative, found a function, and found the derivative of that, it would be f prime prime of t, like this. So basically that's what we've got there. That's sort of how that works. And I just somehow jumped to something I didn't mean to jump to right there. So if you just wait a second. So basically that's where we are. So if you take a derivative of a function of f of t, we'll call that f prime of t. There are other notations that you will sometimes see. There's like a d over dx. We're not going to worry about that for right now, but you calculus people should be familiar with that. But f prime of t is how we'll sort of show it here. So this is called differentiation, is that you would basically say I differentiate f of t to get f prime of t. And that function, f prime of t, is the slope of f of t. And so basically at any point you plug in a value for t, it tells you what the slope is at that point of the original function f of t. Now if we want to go the other way, that we want to go from basically a graph to find the area underneath it, remember that we talked about is that sort of undoing this slope. So if we found a velocity, we use the slope to find acceleration. Now we're going to use the area under to find back to the velocity, sort of what is sometimes called an anti-differentiation. We're doing differentiation backwards. The term we'll use here is going to be integration. And so integration produces what's called an integral of a function. Similarly, gives you the area underneath any function for any region of the function. And so typically if you were going to show that you were going to integrate f of x, the notation that's used, it used sort of this squiggly, almost it's like a stretched s. It actually is a stretched s. It actually stands for sum. And then there's dx afterwards. Basically, the dx is an indicator that there is a derivative in here. We're sort of summing up derivatives to find an area. Because if you want to find an area, what do? You sum up the pieces. It's like, you sort of add up the different pieces to get the area under something. It's like counting tiles on a floor to figure out the area of a room. And so differentiation finds slope, integration finds area. But how is this helpful? So to take a look at that, let's see what we've got. So on this, if we have a distance function, d of t, this is what we're going to start with here. We have this distance function, d of t. We can differentiate it to find its velocity function, since differentiation will give us the slope of a distance function, which is velocity. So we have a distance function, d of t. If we differentiate it, find d prime of t, that will give us the velocity, v of t. That function right there. All right, so that's sort of what we got here. If we differentiate that velocity function, v of t, that will give us an acceleration function, because if we differentiate a velocity function, that will give us the slope of a velocity function, and the slope of a velocity function we said was acceleration. So v prime of t is equal to a of t. Okay? Now let's go the other way. We want to find areas now, so we use integration. So the integration of acceleration function would tell us then the area underneath acceleration, and area underneath acceleration is velocity. So the integration of acceleration will give us a velocity function, and if we integrate a velocity function, it'll give us a distance function. So if you integrate an acceleration function, you get a velocity function. You integrate a velocity function, you get a distance function. And so this is sort of how it works here. So on our previous table where we sort of had distance, velocity, and acceleration, differentiation goes this way, integration goes that way. And so that's how you go from one to the next one. We really aren't going to talk about what happens if you were to actually try to go farther than acceleration. If you were to try to differentiate an acceleration on that one, you'd actually get what's called jerk in that case. Or what happens if you integrate under distance. We're not going to worry about those things. Just for distance, velocity, and acceleration, if you want to go from distance to velocity to acceleration, you differentiate, find the slopes. If you want to get from acceleration to velocity then to distance, you'd integrate, find the areas. And so that's what we've got here. So for this, we move on. So how do we do this? That's the one thing we have not talked about yet. If I do, suppose I have a distance function, d of t, and it's of this following form. d of t is equal to a times t to the n. And so in this case right here, d of t is a distance, so that's your distance right there. A is a constant, just some number, could be -5, could be 30, could be pi. T is the time right up there, and n is just the power of t, just whatever its power is. So if it's t cubed, n would be 3. If it's t to the 5th, n is 5. If it's just t, n would be 1. So that's what we got here. Now, if this is our function, d of t is equal to a t to the n, the derivative d prime of t is going to be written like this. That d of t is equal to a times n, we took the n from the top and brought it down, times t to the n minus 1. So basically, let's suppose we've got an example here. D of t is equal to 2t to the 4th. And so d prime of t, well, the first part is the a is still out front, and so it's still going to be 2 right here. But 2 times, what's next? Times n. N is the power of t, and so that's 4 on this one. So times 4 times the next one, which is said t to the n minus 1. So it's t to the 4 minus 1 is 3. And so my final answer here is going to be 2 times 4 is 8, so 8t cubed. That's my answer. So so if I differentiate d of t, I differentiate 2t to the 4th, I get 8t to the 3rd. That's all it is. And so if I had, let's say I've got another one. I've got d of t is equal to 14x cubed. In this case right here, I'd say that d prime of t, the differential, to differentiate that, then basically I'd say 14 times, bring the 3 down, 3 times, that should be t, not x, times t to the 3 minus 1, t to the 2nd here. So 14 times 3, 28, 42. So this would be that d prime of t would be equal to 42t squared, just like that. That's how you differentiate something. And so that basically means the slope of 14t cubed at any point is 42t squared. And so if I want to find what's the slope at 1 second, what's the slope of this graph at 1 second? I'd say 1, put in 1 for t, and so t1 squared is 1 times 42 is 42. The slope's 42. That's how that works. C is not all that bad, basically, just simple differentials. This is basically calculus here. Now, a couple quick sort of things that seem like there's somewhat exceptions here. Let's say I had d of t was equal to 2t. What happens here? Well, if I want to find my, if I differentiate it like this, d prime of t, that I know I'd have 2 out front. T is to the first power right here, so I bring a 1 down, times t to the, what? 1 minus 1 is 0, t to the 0. But anything to the 0 power is just 1. And so I get 2 times 1 times 1, that's just equal to 2. And so in this case, when I differentiate d of t, where it's 2t, then I just get 2. Typically, you end up with a constant in this case. This happens sometimes. If you have a case where you've got something that is some number times a variable to the power of 1, the variable is just going to disappear. Now it's gone. So that's what you have here. Now, second exception. D of t is equal to 3. Well, first thing, think about this. If d of t is equal to 3, that basically means the object's not moving. Because no matter what t is, d is always 3. This is something that's just sitting still. And so we said before, if you take if you differentiate, take the differential of the distance, then you're going to end up getting a velocity. If you're not moving, what's your velocity? 0. Anytime that you differentiate a constant, it goes to 0. Well, that's not actually right. I shouldn't have put that there. So d of t is 3. Then in this case right here, differentiate that d prime of t is basically going to equal 0. And so when you differentiate a constant, you get 0. That's all you do here. Because if you differentiate a constant, how much is a constant changing? It isn't. That's what makes it a constant. So that's basically what we've got here. And so this is basically how you do differentials on things, how you differentiate stuff. And so let's move on here. So let's suppose we have a case. A particle moves so that its distance from the origin is negative 2t cubed plus 3t plus 4. What are the particle's velocity and acceleration functions? So we know its distance is negative 2t cubed plus 3t plus 4. And so this right here is our d of t right here. So I say that d of t for this is equal to negative 2t cubed plus 3t plus 4. And that's what we have right there. Now, this is my distance function. I want to find first the velocity function. And remember that basically what we're doing is we go distance, velocity, acceleration. If we're differentiating, we are going to go this way. And so if I differentiate my distance function, I will get my velocity function. And so if I find d prime of t, that's equal to v of t. And now I just need to find what this is. So let's look at this first term, negative 2t cubed. The way that you basically do differentiation whenever you have multiple terms is you differentiate each term individually. This works if you're adding or subtracting. Doesn't work if you're multiplying, but if you want to know about that, take calculus. So we just have to do 2t cubed first, then add that to the differential of 3t plus the differential of 4. So 2t cubed, negative 2t cubed. So the negative 2 is still out front. We bring the 3 down. Negative 2 times 3 is negative 6. So then t to the 3 minus 1, t squared. Plus the next one, 3t, that's t to the first power. So 3 times 1 is 3 times t to the 0, really? So that's basically, that one just goes away, because that's just 3. And then plus 4, you differentiate a constant, you get nothing. So we have 6t squared plus 3, that's my velocity function. So I've got my velocity function, no trouble here. Now I want to find my acceleration function. The acceleration function would be the differentiation of the velocity function, which is the second differentiate twice, a double derivative, the second derivative of the distance, and so that's equal to the derivative of the velocity, v prime of t, which is basically going to be the derivative of what we have right here. So negative 6t squared, we'd pull the 2 down, so I get negative 12. And then t to the 2 minus 1. 2 minus 1 is just 1, so t here. Plus 3. 3 is a constant. Take the derivative of it. You basically get a constant. So I end up with that v prime of t is equal to negative 12t. And that would be my acceleration, because the derivative of the velocity gives the acceleration. So this is my final answer here. So my velocity function, v of t, is equal to negative 6t squared plus 3. My acceleration function, a of t, is equal to negative 12t. And so that's basically how you work those out. So onward we go. If that's how to differentiate, the next question would be how to integrate. So let's suppose that we have a velocity function, which is, this is going to be v of t, that's of the following form. So v of t is equal to a times t to the n. Notice it's exactly the same as the last one. A is the constant, t is the time, n is the power of t. So if we want to integrate this, the integral of v of t is then integral of a times t to the n dt. And really the part we only care about is this part inside here and the fact it's an integral right there. The dt you can sort of ignore until you take calculus, if you haven't taken calculus yet. This is going to be equal to a over n plus 1 times t to the n plus 1 plus c. So let's take a look at this, break this down. The a is still out front, the same place it always was in the last case. The a doesn't move around. Now, this time, instead of bringing the n down, since we're doing an antiderivative, we're doing the opposite of differentiating, on that one, we had to multiply it times the power. This time, since we're going the opposite way, we're going to divide it by the power, but instead of being the power that it was before, now it's going to be the power it's about to be. And so basically in this case right here is it's going to be n plus 1 on the bottom, and t's raised the n plus 1 power. So we have that. Now, this last part here, c. c is a constant. This sort of has to be here. The reason why is because we noticed last time that if you basically took the derivative of a constant, you got 0. And so if you undo a derivative, you integrate, you anti-differentiate something, then there's always a possibility that the original thing that you're going back to, what you started with, differentiated it, and now you're going to integrate it back to what it started with, might have had a constant in it. You don't know. And so because you don't know, you've got to put that there's a constant on the end. And so in math, it's just a constant. It's c. But in physics, this c actually means something. So here's basically what it means, is that if you, so we got our standard here, distance, velocity, acceleration, and so we're integrating, so we're going this way, we're going to the left. And so if you're going from acceleration to velocity, if it creates a c, that c is basically the original velocity. It's v naught from all our previous equations right here. If you're going to distance here, is that when you're creating a distance formula, that constant is going to be d naught. That it's the original velocity. And so when finding velocity, if you're finding velocity like here, then c is the initial velocity v naught. When finding distance, c is the initial d naught, initial distance d naught. So let's try another example down here. So we have a of t is equal to 6t squared, and we want to integrate it. So integrate a of t dt and see what we get. And so I have my integral here. I want to integrate 6t squared dt. And so to do this, basically I remember the a is out front still. That's up here. Divided by n plus 1. And so this is 2. 2 plus 1 is 3 times t to the n plus 1, so t to the third, plus c to get it out like that. And so 6 divided by 3 is just 2, so 2t cubed plus c is my answer here. That's how that works. And so let's suppose I had another case here. Let's say I have v of t is equal to, I'll integrate v of t dt. And let's say that v of t is equal to negative 6t to the t to the fourth. Wow, let's write that up here. V of t in this case is negative 6t to the fourth, and I want to integrate this. And so if I integrate this right here, the negative 6 still stays out front. I'm going to basically divide that this time by 4 plus 1, 5, times t to the 1 up from that, to the fifth, plus c. And so this ends up being negative 6t to the fifth plus c. This is basically how it works. If I had a number, let's say I want to say what's the integral of 5 dt. In this case right here, I would say, well, 5 is sort of, you can think of 5 as basically being 5 times t to the 0, right? And so if it's 5 times t to the 0, then to bring this up, what I'm basically doing is 0 plus 1 is just 1. And so it'll be 5 divided by 1 times t to the 1 plus c. And so that's just 5t plus c. Anytime you basically integrate a constant, it's just going to turn into that constant times the variable, t in this case, plus c. That's all you have there. And so that's basically what we do for that one. Let's take a look onward, and let's put this into some application. So an object is dropped at 5 meters per second into a viscous fluid and found to have an acceleration of 10 minus 4t meters per second squared. What are the functions of velocity and distance for this object? So we know, in this case, that our acceleration function is basically going to be a of t is equal to 10 minus 4t right here. So let's basically integrate this. If we integrate 10 minus 4t, this will equal our velocity, because if you integrate acceleration, you get velocity. And so our velocity function then would be, well, we works the same way the other one did, is we can work into it individually. So if I have 10 and I want to integrate it, that's basically what we said, turn it to 10t. Like that. So we have 10t right here. And the next one here is still this negative 4's out front times t to the second. And so it's negative 4 over 2, because it's going to the second, times t to the squared, and then plus a constant. Now in this case we're going to velocity. And so the constant we're going to go to is whatever the original velocity is. And so it's plus c out there. And so v of t right there. So I get 10t minus 4 over 2 is 2. T squared plus c, and my constant we said was just whatever the original velocity is, and it says object dropped at 5 meters per second, so plus 5, like that. And so this is my velocity, 10t minus 2t squared plus 5. That's how it works here. Now the next thing would be to get the distance function. The distance function, d of t, is equal to the integral of the velocity function, which we just found. And so when we do that, so the integral of 10t would be 10 times, so t is going to go from t to the first power to t to the second power, so it would be 10 over 2, that's just 5, times t squared, because the t is going up here. On the next one, it is minus 2t squared, and so it's t squared, it's going to go t cubed, so it's 2 over 3, so minus 2/3 t to the third power, plus our last one is 5, and that's just going to become 5t plus c. In this case right here, c is our original distance. Since basically that d naught is going to work the same way as d naughts always did, we're going to, if we want to measure it from the top of the surface of the liquid, that just becomes 0 right there, and so really we can cross that part out. And so we get a distance function is 5t squared minus 2/3 t cubed plus 5t, and that's sort of what we have there. So that's how you would go ahead and basically work out a differentiation problem like that, or an integration problem. So let's look at sort of an example here. A particle travels away from its starting point is at a distance given by 4t cubed minus 3t squared. And so the first question is, what's the distance of the particle at t equals 17 seconds? Well, this is pretty straightforward here. If you ask just what the distance is, we don't have to do any differentiation or integration. We just have to plug it in. So I've got right on here that that we have 4 times t cubed, and t is 17, so 17 cubed minus 3 times t, 17 seconds squared. And so to find my answer here, all I'd have to do is I'd have to say 4 times 17 cubed, if I can figure out how to do this on this calculator, minus 3 times 17 squared. And in doing that, I get 18,785. And so 18,875 meters right here, assuming that this is in distances in meters. I probably should have put that in there. And so that's the distance right there. All right, no problem. What's the velocity of that particle at t equals 5 seconds? A little more here. To find the velocity, if I have a distance function, I've got to find the slope of that function. That's differentiation. And so to differentiate this, I've got 4t cubed as the first term. So I bring the 3 down, so 4 times 3 is 12. T, now 3 minus 1 is 2, so 12t squared, minus, bring the 2 down, 2 times 3 is 6, 6t, 2 minus 1 is just t, so 12t squared minus 6t. And now I'm going to plug it in. And so I say 12 times 5 squared minus 6 times 5. And so I would say 12 times 5 squared, 25, minus 6 times 5, which is 30, and I get 270. And so in this case right here, what's the velocity of the particle at 5 seconds? It's going 270 meters per second, just like that. Not too bad, not too bad. What about the acceleration? Well, to find the acceleration, I'd have to take my, my velocity function right here and differentiate it again. And so I bring the 2 down. 2 times 12 is 24 times t, 2 minus 1 is just t, minus 6t, that's t to the 1. So I bring a 1 down, so minus 6, then t to the 0 is just 1. And so it's 24t minus 6. And so at 3 seconds, I'd say 24 times 3 minus 6. And so I'd say 24 times 3 minus 6, and I get 66. So this particle is going 66 meters per second squared at that point right there. Not too bad, not too bad. So let's go ahead and move on a little farther on this one right here and see what we've got. So a rocket is launched which has an acceleration of 5.5 t meters per second squared. And so the question first is, what's the acceleration of the rocket 10 seconds after launch? Well, we already know. We've got that the acceleration, and we're asking about this, is at 10 seconds. Acceleration at 10 seconds is basically going to equal 5.5 times 10, because that's our acceleration function. And so the acceleration of the rocket is just 55 meters per second squared. Okay? No problem on that one. How fast is the rocket going at t plus 20? That's 20 seconds after launch. And so how fast? That's a velocity. If I have an acceleration and want to get to the velocity, I've got to integrate it. And so I will take the integral of my 5.5 t dt. And that's going to be equal to my velocity. And so if I do this, that means I know I have 5.5 is still out front. T is going to go from t to the first power to the second power, so it's over 2. And then t squared plus c. And so let's see if we can get this out here. So this is 5.5 over 2 is 2.75 t squared plus the original velocity. Well, this rocket's being launched. Typically that would mean it's staying still. So that c, in this case, my original velocity is 0. So 2.75 t squared. And so to find my answer, I'd say 2.75 times 20 seconds, my time, 20 squared. So 2.75 times 20 squared gives me 1,100. So this is going 1,100 meters per second, 20 seconds after we started. Next question: how far away is the rocket after a minute? How far is a distance question? And so to find a distance question, I've got to integrate my last one here. I end up at 2.75 t squared was my velocity function. And so if I want to find my distance, I've got to integrate that. So 2.75 t squared dt. So I want to go from, I start off with 2.75 still. That's still here. I want to go from 2 to 3. I'm raising the power. That's what you do when you integrate. So this will be over 3 because I'm going to the third power. T cubed plus C. And so 2.75 divided by 3 gives me 0.9166. 0.9166 times T cubed. The original distance of this rocket right here, well, it was originally on the launch pad, so it was originally 0. So this is just my function right here, 0.9166 T cubed. And now I'm asking about what happens after a minute. That's 60 seconds. And so I say 0.9166 times 60 cubed. That is a cube right there. And so 9.9166 times 60 to the third power. And I get that this rocket, after a minute, is 197,985.6 meters away. So 197,985 meters is how far the rocket is away after a minute. And that's how you might work that out. Now, one last example before we finish things up. And this one sort of ties everything together. Earlier, we looked at basically our distance equation. So let's talk about what happens if we say we have an object that has a constant acceleration. And this constant acceleration is quite simply just going to be a. Just that's a variable here is that it is constant, but acceleration is a. The initial velocity of this object is v naught and has an initial distance of d naught. So the question is, what's the object's distance function? In this case right here, we start off with an acceleration. And so our acceleration, a of t, is just equal to a. So if I wanted to find the velocity, v of t, what I'd have to do is I'd have to integrate, that's a horrible integral sign, a of t, which means I'm integrating a. And now if I integrate a, this is basically a times basically t to the 0. And so if you're integrating t to the 0, that basically means I'm going to end up with, there's a 1 out front already, so that's still there. I'm going to go from t to the 0 to t to the 1. So 1 divided by 1 is just 1, nothing here. So I just have, and then a to the, sorry, I'm not paying attention here. This right now is a to the first, really, right? So I want to go to a to the second. And so I have 1 out front because there's nothing in front of the a. It's just 1a divided by 2, so it's 1 half a. Make sure I'm getting this one right here. So this is a, never mind, I'm not paying attention. Let me go back to where we had right here. Ignore what I just said. So I have the integral of a of t dt. And this is equal to a dt. A is a constant, it's a number, which basically means I have t to the 0. And so if I have t to the 0, this is my number out front is a. I want to go to t to the first, and so a divided by 1 is just this one right here, so I get a of t plus c is what I get for this one right here. So c in this case, since I just found a velocity function, c is the constant which you'd have for the original velocity. The original velocity here, it tells us is v naught, and so I have at plus v naught is what I have for this one right here. This is my velocity function. And so I've got my velocity function. My next step is it asks for the distance function. The distance function, d of t, is basically equal to the integration of my velocity function, which I just found was equal to at plus v naught dt. So my distance function then, d of t, would be the integration of a to the t here. So first thing, I want to go, I have a out front, that's my constant out front here, and I'm going to go t from the first power, I'm going to go up 1, so I'm going to the second, and so therefore I have to have a 1/2 out here. That's why I was getting ahead of myself earlier here. So I have 1/2 times a, but now it's going to be t to the second right up here, because t's gone up, plus my next one, v naught's a constant, it's still out front. Right now it's just v naught times basically 1, t to the 0, so I'm going to go to t to the first, and that means v naught over 1 is just this one, and then plus c. Now since we're talking about a distance here, my initial distance, it says, is d naught, and so that I'm going to get my distance function, d of t, is equal to 1/2 at squared plus v naught times t plus d naught. That's my answer. Have you seen that before? That is our distance equation we came up with. This distance equation is a simple consequence of doing calculus to the fact that we have an original acceleration a, an original velocity v naught, and original distance d naught, is that we can get that same answer that we've been relying on using this method. And that basically is how you